morning. I'm Erica Bierstrom. I'm the dairy educator for Kewaunee, Doring, Brown counties, and Tina is joining today from Fond du Lac, Sheboygan, Ozaukee, and Washington. And today we'll be talking to you about feeding efficiency, dietary impacts on manure, carbon, and methane. Agriculture is a contributor to gas emissions, and of all of the greenhouse gas emissions that agriculture, or that all of them that are produced, agriculture produces about 10% of the total greenhouse gas emissions. Through that, our livestock produce greenhouse gas emissions through enteric fermentation and through the manure management as farmers, and how that's managed and how we apply it and take care of it out in the fields. Also through agriculture soils, and how, again, once that manure is on the fields, and things we don't necessarily worry about too much here is rice production and burning crop residue. Of course, in South America, there's a lot more burning crop residue down there, where they're burning to produce more cropland for crops such as soybeans. Through the agriculture emissions in greenhouse gas emissions, about a quarter of that is, again, through the agriculture sector. There are about 94 million cattle in the United States, and about 9.5 million of those are dairy cattle. When we look at the types of agriculture and what kind of gas is produced, we have our cow here. Our cow produces methane from both ends. She burps, and it comes out through the manure and through farts, essentially. She produces the methane, the nitrous oxide, and the carbon dioxide. Those, again, as I said in the previous slide, manure management, enteric fermentation, crop and soil management, those three aspects produce our carbon dioxide, which is about 1%, the methane, 41%, and nitrous oxide, something we probably don't think about that much. We usually think about methane and carbon dioxide. So nitrous oxide is actually the biggest type of gas that's produced. And nitrous oxide is the largest contributor to the ozone depletion. Essentially, what it comes down to is the less feed is digestible, the more gas that cow produces. And feeding to improve efficiency and performance is not only improving your bottom line, improving the production, the efficiency of the cow eating that feed. You have to feed her less. Everything is just more efficient. It also reduces the amount of greenhouse gases she produces. Livestock, urine, and manure are significant sources of methane and nitrous oxide. And ruminants, this is a surprising number, excrete 75 to 95% of the nitrogen they ingest. We think about how much corn we're putting into a cow and how much of that is digestible. And you can see that, when you see a cow eat corn and it comes out completely intact, you're not doing something correct. With the nitrogen the cow is excreting, you're not really seeing that. And it's a little bit harder to grasp. And through that, she's reducing her urinary, we want to reduce urinary nitrogen. We want to utilize higher protein or energy to protein ratio forages. We can breed cows to be more efficient, and we can balance that high protein forages with high energy supplements. The dietary impacts on carbon. The formulation of diet influences the carbon-nitrogen ratio of manure, which ultimately impacts the amount of methane that cow produces. We did quite a bit of research on this, and we were having trouble actually finding a lot of research on carbons, because most of the research is done on the methane excretion of cows. And so we were looking at how carbon impacts agriculture. Our relevant forms when we look at carbon is the methane and the carbon dioxide. And most of this research is on, again, the methane emissions and not so much yet on carbon dioxide. The biogenic carbon cycle. So this is something that we may have seen and maybe not necessarily paid much attention to, but we know that when a cow eats carbohydrates, she uses those carbohydrates, and through enteric fermentation, she produces methane. And methane is in our atmosphere for quite a while. And after 12 years, it is converted to carbon dioxide. So it's out there for 12 years. There's 94 million cattle out there. There's a lot of carbon dioxide a lot of methane in our atmosphere. And carbon dioxide is removed from our atmosphere through photosynthesis. So our plants are converting this, they're absorbing the carbon dioxide through photosynthesis, and then our cow turns around, she eats that plant, and we go through this circle again. So it is a cycle. It's important to have all the pieces to it. We just need to figure out how to reduce that amount of greenhouse gas that's coming out of that cow. And a lot of it is that enteric fermentation that we need to get a better grasp on. And so reducing the strategies for carbon, we need to balance the ratios. A balanced, healthy rumen is going to produce less gas. Feed your cattle to the best of their genetic potential, and remove them from the herd if they're not living up to their best genetic potential. We want to feed this healthy rumen. We want to have correct energy, we have correct protein, and correct fiber ratios. And ensuring these livestock are fed to achieve their maximum genetic potential in milk production is the best way to reduce the amount of gases that these animals are producing.
The last part of this presentation is about the dietary impacts on methane when it comes to our great dairy cow. 98% of the enteric methane emissions, the methane produced in the rumen and then excreted as through a burp or a belching, comes from dairy cattle and beef cattle. So 98% of the enteric production of methane comes through their diet and through those larger animals. The other 2% are more of the small ruminant animals, the goats, the sheep, and other types, but mainly because of the large population of dairy and beef we have in the world, we see a lot of that impact on methane and maybe a possibility to reduce the methane in these animals. So we know that diet is the biggest influencer of emissions of methane. And when we look at the rumen, which nature has developed this really powerhouse of synergy of microbes in the dairy cow, but there is a huge rumen microbial population that really takes and do different functions within the rumen to digest the feeds, produce microbial protein, and be able to have the cow take diets and feed stuff that we as humans can't consume or digest and make into a healthy product. So when we look at the rumen microbial population, we have carbohydrate-rich diets and cellulose-rich diets. So the grains diet or the forage diets. And the rumen population in those animals, in the rumen, really adapt themselves to whether it's a grains diet or a forage diet. So when we look at a beef animal versus a dairy animal, we'll see a higher population of the cellulose type microbial population. And then when we look at the carbohydrate rich diets or the grains diets, we'll tend to see different types of rumen microbes in the beef animal. And when we look at this animal, beef or dairy, they're taking in plant material or feed stuff. And then bacterial digestion through the microbes are breaking it down, fermenting that feed stuff, producing microbial protein, and breaking it down into volatile fatty acids and other nutrients so that it can be digested later in the GI tract. And part of that digestion and fermentation is the products of hydrogen and carbon dioxide. And when we have these type of chemicals or compounds in the rumen, there are other microbes that are methanogens, those that produce methane, that takes the hydrogen and carbon dioxide to produce methane, which then is released through the belching of our animal. And we do have lots of rumen microbes that produce methane. And when we think about the rumen population, we have bacteria, we have protozoa, we have fungi, and they ferment many of the carbohydrates and the forages in our rumen. And then when they ferment and digest, we have reducing equivalents. We have the amino acids and the protein synthesis with the microbial protein. We have lipid synthesis and biohydrogenation so that we get some energy down into the small intestine for absorption. But then also we have, again, the hydrogen and the and the methane produced by our methanogens, those that produce bacteria and microbes that produce methane. We have free living type of pathogens or microbes in the population. And then just remember, when we talk a little bit later, we have an endosymbiotic. So we have some microbes that live within the protozoa that we have in the rumen that can produce methane as well. So kind of remember this track here just a little bit for a couple of slides later. And when we look at research from several years back, there's potential areas of reduction of methane. Erica alluded to it earlier with genetic selection on feed efficiency in high producing animals to utilize those nutrients better. Feeding and nutrition, our diets, that we do have nutrient absorption and provide the proper nutrition, not overfeeding nitrogen, or other types of feedstuffs. We do also have rumen modifiers, which we'll discuss a little bit more, and other management practices, including feed additives. So when we're looking at strategies to reduce methane, really we want to feed high quality, high digestible forage or grains. And this will help because of the interaction, the biochemistry in the rumen. We're wanting to produce more propionate acid, not acetic acid, when we produce some of those volatile fatty acids, because those acetic acids helps with the pathways in making more of the methane. Especially with the protozoa that love acetic acid or the acetic volatile fatty acid, they will in turn support the protozoa, who then later down in the pathway promotes methane production. Utilizing ionophores, we see this more in the beef industry than in the dairy industry. Not a lot of consistent research, but there is some potential there with ionophores. Again, utilizing and increasing feed efficiency, more on the grains heavy diets than we see on the forage heavy diets. Also, a strategy is grinding and pelleting of forages, and this helps with breaking it down into smaller particle size so that we have an increased rate of passage of those feedstuffs going through the rumen into the small intestine, leaving less opportunity for methane to produce. And then we also know strategies like utilizing dietary fats. Dietary fats can be toxic to them, reducing the methanogens, thus reducing the amount of methane. But the key here is when we look at reducing strategies, we also have to outweigh animal performance, animal welfare. We don't want toxicity to the animal. Obviously, efficiency, financial aspect of forages, and keeping that rumen healthy overall. So none of these strategies is a fix-all situation, but there are possibilities working with your nutritionist if you're looking at not only reducing methane production, but also increasing the feed efficiency so that your animals are utilizing the feed better. Here is a chart by Larry Chase from a literature review done by NAP in 2014, just some examples of some management impacts on methane emissions. We could see decreases in methane per energy corrected milk when we increase dry matter intake. We decrease particle size and the processing of the grain, maintaining rumen pH less than 5.5, again, supporting those microbes that are not methanogens that produce methane. Feeding higher levels of grain, again, we're looking at producing more of the propionics, not the acetate acids for volatile fatty acids. Forage quality, type of forage and selection, and fat feeding. But I think when we look at all of these things, these are things that are already being done on dairy operations that help you with your feed efficiency, high levels of production, and maintaining a healthy cow. When we look at feed additives to reduce methane, there's two types of feed additives. There's the methane inhibitors, and then there's the rumen fermentation modifiers. Methane inhibitors really block or inhibit the formation of methane. Some products here you may have heard of is this 3-NOP or nitrooxypropanol, which is been accepted in Chile and Brazil, and right now going through experimental research in Canada. And what it does is interrupts the enzymatic process of methane production. UC Davis has been looking at bromoform or red seaweed. We're seeing that a little bit more, seeing an 80% reduction in beef cattle when it comes to methane production. So there is some promise there, but obviously that does cross over to the dairy operation. Is it even feasible, first from a monetary perspective, having seaweed shipped here to the Midwest, but also think about this increased CO2, carbon dioxide, that would be produced in transportation to get that type of feed product here to the Midwest. offsetting what we could possibly save in reduced methane production. Nitrates as a feed additive is a possibility as well. Again, nitrates here allow the microbes, disrupts the microbes again with the methogens, and then also allows that pathway from production of CO2 and H2 to methane. It actually allows that H2 or the hydrogen be more switched over to nitrous oxide or nitrogen, so that way we don't have as much methane, but then again we're causing another greenhouse gas we produce, but again the nitrates are not as high as what we see in the methane. Rumen fermentation modifiers is mainly protecting that rumen protein. So we've used that to get rumen protein protected and into the small intestine. So again, ionophores can be used. Tannins, there's some limited research on tannins. That's an anti-nutritional factor, so it decreases palatability, may cause issues, toxicity to the cow. So again, that's just some research that needs to be done, as well as essential oils. And again, that's about encapsulating that protein, protecting that protein, changing the structure of the protein so that those less desirable microbes are not digesting them. And then later we're seeing it produce into methane. Now, are there other approaches? So again, I talked about that pathway, or those bacteria, the microbes, fungi that are in the rumen. Again, can we look at removing protozoa from the rumen, or removing a large amount, so that we can break down that pathway, disrupt that pathway? That little critter there is responsible for a lot of the methane being produced in the end products. Encouragement of the ketogenic bacteria to grow so that we don't have as much of those bacteria that can help produce the methane. And then some research, again, possibility is a vaccinate to stimulate antibodies against methanogens, those bacteria or microbes that produce methane. But we have to consider the concerns. Again, this is where a lot of the research is occurring to help answer these questions, that doing some of these approaches, even the ones I mentioned earlier, potential toxicity to rumen microbes and to the cow. So we don't want to interrupt the cow's health, welfare, or productivity. We'll see different effects of microbial adaptation of rumen, volatility, expense of the product being shipped in as it fits into your farm management program, and how do we deliver some of these types of approaches to cows on pasture. Cows on pasture are a higher culprit of producing methane than those in confinement because of their diet being more of the forages, and in some cases lower quality forages when we get down to late summer. So finally, I just wanted to wrap up real quick. And the thing about agriculture and greenhouse emissions, it really comes down to feed efficiency. What can we do to maximize the efficiency of the rumen to digest those nutrients so that we can not only reduce enteric fermentation and the production of methane and reduce the amount of some of those end products like nitrogen going through the cow to manure, but how can we increase the feed efficiency to not only reduce greenhouse emissions, but also to improve productivity, animal welfare, and financially the bottom line when it comes to using a lot of these nutrients and feedstuffs, so that we know it's going to where we want it in the development of milk and not necessarily going in one end